My name's Andrew Daley. I'm a professor at the University of Oxford, and I'm an External Advisory Board member for the PASQuanS project. My work is in theoretical quantum optics and quantum simulation, and I've worked for a number of years thinking about the architectures and applications for quantum simulation platforms and also for quantum computing. The idea of quantum advantage is that we have a quantum device that's able to effectively solve a problem that we might be interested in, either in science or beyond science, either faster or in some sense better, with fewer energy resources or giving a better answer to the question than any known existing conventional technique. Where we are with quantum simulation platforms is that we already know for certain types of scientific problems, in particular when we have highly out of equilibrium dynamics in models that are native to these simulation platforms, that we're able to capture dynamics that we don't have any known way to capture in a simulation on a classical supercomputer, and where we also know that if we try to do the same thing using any known algorithms for fault-tolerant digital quantum computers, that we would need extremely large amounts of resource that are well beyond what people are able to produce in current technologies. There are a number of challenges around really applying quantum simulation platforms to problems, especially that go beyond sort of the basic science that we do on these platforms. And some of those really involve understanding in more detail the imperfections of the platforms, understanding also how we verify solutions. If we've got solutions to a problem that we can't solve any other way, how do we know that we can trust the solution that's been given to us by a quantum simulation platform? Same is true, of course, in digital quantum computing. And so part of the theoretical frameworks are really understanding this question of benchmarking and verification. The other really important element of this is in really identifying where the applications are going to come, where we might expect to see a quantum advantage. And for things beyond basic science in these platforms, that's very much an open question across the whole quantum computing and simulation landscape. And there, it's extraordinarily important to bring together people who really understand the capabilities of these platforms with experts in the areas where we want to apply them. And this can be, for example, people who are experts in materials or quantum chemistry. And as we try to take these things beyond quantum problems, also finding experts in fluid dynamics or in optimization who really understand where the challenges are for existing techniques and therefore where the opportunities might be for these architectures. And the big open science questions is, can we work in an interdisciplinary way between quantum scientists and application specialists to understand where those opportunities are, to understand where the biggest impact could come from these things, and then to pursue that, to adapt the architectures we have for the experiments, to implement problems where we think there's a real opportunity, and then to really push this towards industrial applications eventually. So the really exciting thing about PASQuanS is that we have a number of the very best people in the world in terms of both the theorists and the experimentalists. We have some of the leading experimental platforms in the world across a variety of different architectures, and it's very exciting to bring together people with different expertise. Also bringing in industrial partners that are providing new laser systems and technologies that will underpin future generations of these platforms. And then on the theory side, leveraging expertise also from subject matter experts in industry and the application areas. This bringing together of people with complementary skills who are at the forefront of what they're doing internationally provides a great environment for new ideas and for genuine new opportunities to make real-world impact with quantum simulators. The impact of this, I think, is going to be in setting new directions, new pathways to impact of the platforms, and generating new scientific ideas. So I think that what these platforms will look like in 10 years from now is probably quite different to where we are today, and I think you'll see the beginnings of a lot of things coming out of this program, both on a basic science level and with this orientation towards the question of where can we make the biggest impact and how can we make these things useful beyond basic science.